Okay guys, let's take a look at our lesson for today. We are looking at day 2, and here's where we start talking about area, the area of a polar curve. So let's first of all start by this is the thought process behind how the formula was created. We take a look at this. Using the area of a sector, we're probably familiar with this concept or should be familiar. If theta is measured in radians, then that puts us to this formula. And when we simplify the formula, we come up with this area of a sector formula. And so that's how our our area of a polar curve is created. That's how they get the formula. So it takes us to this. This is our formula. Actually, it's fairly straightforward. I will tell you probably the most common mistake that I see is forgetting to put this 1/2 and forgetting to square. Those are the two most common mistakes that I see in using this formula. So just be made aware. Be sure we have the half and that we take r squared. Now, as far as finding r, in contrast to what we've done before, finding r is actually pretty easy. I mean, if you look, they give you r. So you don't have to do any kind of measurements like we were doing with regular area or volume. You don't have to do any of that. You actually have the r given to you. Probably the most challenging part, I would think, is determining the bounds. Determining the bounds of your integral. How do I decide where it starts and where it ends? And that's where the graphing comes in handy. So let's take a look at this graph. This is similar to the one that we graphed a few days ago, this 2 plus 2 sine theta. And just like I was talking to y'all before, I would do a Cartesian graph and use that as my t-chart. So let's see, we have amplitude is 2 and it's shifted up 2. So our axis would be here at 2. And then it's shifted up 2. Regular period. So we would have our regular pi over 2, pi, 3 pi over 2 and 2 pi. And it's sine, so it's going to start at the axis. So, and then go up, and then down. Okay, so here would be our graph. So translating that to a polar graph, let's see, we start out at angle measure 0, we'd be at 2. Then at pi over 2, we go to 4. So we connect those with a curve. Notice how my r value is positive. So I am in the proper quadrant. If my angle measure is in the first quadrant and my r value is positive, I am in the first quadrant. And just a reminder from last year. So then we go to pi, and at pi we're at 2. Again, my r value is positive, so my curve is in the proper quadrant that the angle is in. We go to 3 pi over 2, which is at 0. And remembering from yesterday, it's not a straight line thing. The between pi and 3 pi over 2, so in the third quadrant, the r value is positive. That means we are in the third quadrant. So it goes like that. And then again, between 3 pi over 2 and 2 pi, we're in the fourth quadrant, and so is the r value is positive. So it looks like that. All right. So when we set up our integral, we have the 1/2 out there. And through this graphing, we have discovered that we start it at 0 and end it at 2 pi, we have one full revolution. We have one full picture of the graph. So we would start it at 0, our integral, and end it at 2 pi. Our formula calls for us to square the r. So 2 plus 2 sine theta is going to be squared. and that is the integral that we're going to work. Now before I get into the integral, to integrating that, a lot of books show what they call radial lines. Some students get really confused with how the area is created. So if we start, here at 0, and we kind of follow the graph as it's created, that's how the area is. It's kind of like accumulating the area as it goes. It's picking it up as it goes, and it'll swing all the way around to pick up all of the area. So that's just a visual that a lot of textbooks like to use to show how the area is generated. Okay, so let's work on our integral. First thing we need to do is FOIL that. So we're going to get 1/2 integral 0 to pi. So that's going to give me 4 plus, what would that be, 8 sine theta plus 4 sine squared. Okay, we're probably pretty happy with the 4 and the 8 sine. Maybe a little tentative to the 4 sine squared. Hopefully we remember our double angle formulas, which we solved for sine squared and cosine squared. Remember that from last unit? That's what we're going to have to use here. In order to integrate sine squared, we're going to have to change it. We can't integrate it like it is. So, does anybody remember? Remember the formula is 1/2? Perfect. Over 2, that's right. The sine one is the minus one, right? The one minus cosine 2 theta. The cosine one is the plus one. They both look exactly the same. One's minus and one's plus, and we do have to remember that. That's not going away. So we're going to replace this with, let's get there. So I have 4 plus 8 sine plus, I have a 4. Then we're going to use our formula for sine squared, which is 1/2, and that's 1 minus cosine 2 theta, d theta. Okay? So what we would do is distribute here. So I'm going to get 4 times 1/2 is 2, and that gives me 2 times 1 is 2. So that 4 is going to, just to make our integration easier, I'm just trying to clean it up a bit to make our integration easier. So I'm going to have a 4 plus 2. That's going to give me 6 plus 8 sine theta. And then this, let's see, it'd be 2, so minus 2 cosine 2 theta. Alright. I'm going to move up a little higher so you can see. Is everybody with me to here? Okay, I'm just going to do a little bit of erasing and move the integral up. Just a few more steps. Okay. So let's do the antiderivative. So we have our 1/2 there. That's going to give me 6 theta. And sine, what would we have taken the derivative of to get a positive sign? Would have been a negative cosine, so minus 8 cosine theta. And similarly, we need to get a 2, well, let's not worry about the 2 right now. We need to get a cosine 2 theta, a negative cosine 2 theta. And so we would have integrated that. Now let's think about this with the little baby u sub for this part right here. What constant am I going to come out with? And I don't have to write it down. I can do it in my head. For this little baby u sub, what constant is going to come out of that? A 2 or a half? A half, right? Because I would say u equals 2 theta, du equals 2, and I don't have I have a 2 in there, but I could divide it out and give me a half. That's going to make this go away. So 2 times a half would be 1. So that leaves me negative sine 2 theta. And that we're going to integrate from 0 to 2 pi. So here our unit circle values are pretty important. Okay, which I'm sure we probably have those down without a problem, right? We're great on unit circle. So we're going to put the 2 pi in for theta. So I have a half times. So 6 times 2 pi is going to give me 12 pi. Then let's see, cosine of 2 pi is 1, right? And that gives me 1 times negative 8 is negative 8. Sine of 4 pi, that's just 0, isn't it? Sine of 4 pi is 0. So minus 0. Okay, let's put the 0 in. 6 times 0, well that's nice, that's 0. Cosine of 0 is 1. So 1 times negative 8 is negative 8. And then sine of 0 is 0. So let's see what's going on. It looks like the 8's are going away, and I'm left with 6 pi. And that's the area of this polar curve. Okay, we okay so far? The other 2 examples, we're actually not going to go through the integration part. We're going to go through the graphing and setup, but we're not going to go through the integration on the other 2 on the other page. Is everybody okay with the integration? That's just a typical integration. It's probably going to end up with some kind of a squared. You're probably going to have to use those formulas. You need to bring them back to the forefront of your memory. Okay? All right, let's look at our next slide. Okay, so we want to sketch and set up an integral expression to find the area of 1 petal of r equals 2 sine 3 theta. Alright, so we're going to do the setup. We're not going to evaluate. Okay, so let's go over here. And again, I like to draw my t-chart as just a Cartesian coordinate graph. 3 theta is... that changes the period, right? It doesn't increase the period by 3. Do you remember what it does? Yeah, it's pi over 3, so it squishes it together. It's a third of the normal period. So I'm going to actually do my chart by 6, by 1 pi over 6, and so forth to try to get all that in there. So we have 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, and 6 pi over 6. I'm hoping that that's going to be enough to get this drawn. We shall see. So it's sine, and we are at an amplitude of 2. So sine has a start at the axis, and then go up, and then down, down, up. Okay, so it looks like this. Okay, now this one is pretty difficult to graph, but I need you to get a feel for it for several reasons, and I'll explain as I go. Let's kind of split it into quadrants. Well, just to help us with the graph. So to pi over 2, this is quadrant 1, and that's quadrant 2. We may have to do more. We'll just see. We may have to do more of it. But let's see if that's enough. So at angle measure 0, I'm at 0. At angle measure pi over 6, which is right in here, I'm at 2. So pi over 6 would be somewhere in there. Okay, how did I know to go under? Well, because I'm going from 0 to pi over 6, which is this space right in here. So I'm going up like that. From pi over 6 to 3 pi, so 3 pi, pi over 3 would be right here, and I'm going back to 0, and that is my first petal. Now, I can go ahead and write the expression for the first petal, and so let's do that. 0 to pi over 3, my formula says it's a half, and then I square it, 2 sine 3 theta squared. Okay, but I need to finish the graph. I'm going to explain why to you in just a moment. We need to go ahead and finish it just to for several reasons. Well, let's go ahead and finish it, and then we'll talk about it. So I'm at pi over 3 at 0, but look where the R now is dropping below the x-axis. R is now negative. R is negative. And so my angle measure is in the first quadrant, but my R measure is negative. Okay, so visualize this. My angle measure is over here, but my R measure is negative, so it puts me into the third quadrant. All right, so this pedal right here is going between pi over 3 and 2 pi, which is this space right here, is going to put me in R down here. The pedal is going to be right here. Okay? And at pi over 2, which is this, I'm at negative 2, which is here. So it puts me like that. That's what's happening between pi over 3 and pi over 2. Now, after pi over 2, we have gone into the second quadrant now. And we are negative. Our angle measure is in the second quadrant, but our R measure is negative, which means the pedal is over here in the fourth quadrant. And we go up, and we have the completion of our second pedal right here. Okay, at 2 pi over 3. So now I am all positive R's. I'm in my second quadrant. So at 5 pi over 6, which is down here, so my other pedal would be here. Okay, so there's a couple of things I want you to notice. I want you to notice that the start and the stop of each pedal we can actually read off of the Cartesian chart. You see that? My first pedal started at 0 and ended at pi over 3. My second pedal started at pi over 3 and ended at 2 pi over 3. We see the pattern there? I actually can see all three pedals on my Cartesian graph. So, I might draw this. Here's a quiz question. I may draw this, give you the equation, and shade this pedal. And ask you, how would I find the area of this particular pedal? That would be why we would need to know starts and stops. So you can probably guess you're going to get a question like that. Okay? How would you find the area of a particular pedal? Alright, so here's our area. If we wanted to find the area of one pedal and we didn't care which one, that's the one I would use. The first one. Alright, our last one is, we're going to do the same kind of thing. We're going to draw our Cartesian coordinates and then set up our integral. Here we have for cosine 2 theta. So the 2 theta, remember it changes our period half. So by pi we would have done one full cycle of cosine. So I'm going to do just kind of some big sections here. Pi over 2, pi, 3 pi over 2, and 2 pi. Our amplitude is 4. And so we are looking at cosine, and cosine starts here at 1. It's going to go like this. I'm not drawing in all of them. I'm hoping you can see and follow with me. So it does one full cycle at pi. Looks like that. And then it keeps, we're going to keep going here. And here's my second cycle. Alright, this one I'm going to split into quadrants, so hopefully it'll help us visualize it a little better. That's quadrant 1, that's quadrant 2, that's quadrant 3, and that's quadrant 4. Okay, the ones that have negative R's are the ones that I think are trickiest because it just kind of puts you everywhere. So let's see what's going on. When I'm in quadrant 1 at an angle measure of 0, I start out at 4. And by the time I get to pi over 4 in the middle of this, I'm at 0. Okay? I'm at 0. And so I'm right here. Now I go to a negative R. My angle measure is in the first quadrant, but I have a negative R. So where is my petal going to be? In the third quadrant, right? It's going to shoot me across here. And it's going to take me to the third quadrant. And it's going to take me down here. At pi over 4, I'm at negative 4. So here, excuse me, at pi over 2, I'm at negative 4, which just puts me right here. So I have completed quadrant 1. Quadrant 1 is done. I don't even have a full flat petal yet, do I? I don't have a full one yet. I couldn't just say, oh, well, this is 0 to, one complete petal is 0 to 2 to pi over 2. I can't say that because it's 2 halves. All right, so now let's go to quadrant 2. I start out negative in quadrant 2, so that means I'm in quadrant 4. It brings me back up to 0, which is right here. And now I'm in quadrant 2, and it brings me at C pi, we're going to be at 4. So it brings me right here. Okay. Now I'm done with quadrant 2. I'm moving to quadrant 3. Quadrant 3, I'm in the positive. So in the first part of quadrant 3, my R value is positive. So I'm in quadrant 3. That finishes this petal. And then the last part of quadrant 3, I'm negative. So that puts me in quadrant 1, right? And so at 3 pi over 2, I am a negative 4. So it's going to put me back up here. Okay. All right, so we're done with quadrant 3. We're moving to quadrant 4. The first part of quadrant 4, we're as a negative R, so we're going to be in quadrant 2. That finishes this petal. And then it brings us back to here. Now, these do, if we look at these zeros right here, they still tell me the start and stop of the petals, right? They still tell me the start and the stop of the petals. This one is a half petal and this one is a half. If I wanted to do the area of this particular petal, I would need to push it back to negative pi over 4. Okay? So I picked this first one right here to use as my bounds. It just says one petal, so it doesn't really matter which one you pick. So I just picked the first full one, and that's from pi over 4 to 3 pi over 4. And it's half r squared, so it's 4 cosine 2 theta squared. And that would give me one petal. But again, a really good exercise would be shading one of these petals and asking you, if I wanted the area of this particular petal, what would my bounds be? Okay? All right.